Hello, my name is Branka Dimitrijević. This is a recording of the seminar that should have taken place on 19th of October 2011, but couldn't because of the power cut in Glasgow. However, our speakers, Mr. Douglas Prentice of GeoCapita and Dr. Aymeric Girard, who is energy and environment consultant, have stayed with us, and we have prepared this recording of the seminar. I should mention that CIC Start Online seminars and webinars disseminate the outcomes of the feasibility studies and academic consultancy organized through our project. The project supports collaboration between 7 Scottish universities and small to medium-sized enterprises in Scotland in developing innovations for more sustainable building design and refurbishment. The project is funded by European Regional Development Fund and CIC program of Scottish Government. To date, we have produced 10 webinars and 23 conference videos and published 8 issues of quarterly online magazine Innovation Review. During the summer months, we developed a searchable knowledge base on our website. The title of the seminar that you are watching now is Optimisation of Economic, Environmental and Energy Savings in Buildings. These are the outcomes of the feasibility study that was undertaken by the researchers at Edinburgh Napier University in collaboration with GeoCapita. And the speakers are Mr. Douglas Prentice and Dr. Aymeric Girard. Mr. Prentice, I would kindly ask you to start your presentation.
Branka, thank you very much and welcome everyone. And I'm sorry that everyone that wished to attend via the webinar is unable to be present because of the power cut, but no doubt they will be able to view the video online later. So thank you, Branka and colleagues. The original idea for this project came from, in fact, 2 discussions. One was with Branka Dimitrijević of CIC Start, and the other was with Professor Tariq Muneer of Edinburgh Napier University around the triple E delivery of sustainable buildings. In other words, improving the energy, the economic performance and the environmental costs of buildings, both new buildings and retrofit buildings. So out of this discussion came the concept of commissioning some research work through CIC Start from Edinburgh Napier University to formulate a software methodology for analysing the triple E performance of housing and commercial buildings. The application of this output is designed to be applied primarily to owners and operators of housing in the first instance. So this will include social landlords, housing associations, cooperative housing associations in the first instance, both for an evaluation of the performance of their existing housing stock and also for optimisation of the design of the renewable energy installation on new build housing. And we have a number of housing associations in Scotland and in England, and possibly housing cooperatives internationally with whom we are in discussions with regard to assisting them in the retrofit and the new build of their housing using the software provided under the CIC Start facility. Secondly, the application is to small self-build groups, cooperative self-build groups, self-build consortia, who would like to build their own private housing and need advice as to the energy, financial and carbon optimization of the design of the renewable energy installations. Beyond that, we foresee, but are not yet engaged with, providing this software solution to small-scale developers, private sector developers of residential development, and possibly in the longer term, commercial property managers, commercial property investment funds who wish to optimize the performance of their existing portfolio of buildings, and also to property managers. So in fact, there is potentially a very large application for this Kickstart funded research, both within Scotland, beyond Scotland, in the rest of the UK, and indeed beyond the rest of the UK to several other countries in the world. For example, we are currently evaluating the possibility of a project in Sofia in Bulgaria for the creation of sustainable, affordable housing to house Romani gypsies on the outskirts of Sofia, in a project supported by United Nations Economic Commission for Europe, the government of Bulgaria and the government of Sofia. So the potential application of the Kickstart funded project, the Napier research, is potentially of an international dimension. So I would welcome questions later, but again, I would like very much to thank Branka Dimitrievich for supporting this project, Professor Tariq Muneer for agreeing that Napier University would provide the academic partner, and for Dr. Aymeric Girard for the actual design of the software. So thank you very much.
Thank you very much, Douglas. And now I would like to invite Dr. Aymeric Girard to start his presentation.
So I'm going to basically talk through for the next 40 minutes about optimization of the economic, environmental, and energy savings in buildings. What we've done, we've carried out at Edinburgh Napier for GeoCapita, and this was involving Wahid Irshad, a PhD research student at Napier, and Professor Tariq Muneer. So starting on the slide 1 with the agenda, we're going to look at the different backgrounds, what we've got on the different projects, the aims of the project. So looking at what we're going to discuss about and the methodology adopted, ending up with the experiments and the simulation. So I'll come into the detail of all the different parts of the project, looking at the energy, environment, and economy that Douglas mentioned earlier on. We'll look then at the results of the simulation. So why have we done this work at the beginning? First of all, we want to make sure that there is a good reason behind this. So the legislation, first of all, is changing. So we look at the different timelines. Then we've got like a lot of pressure, as you've probably seen over the recent years or over the past 30 years. Oil prices are likely to increase. Electricity bills, as a result, as a byproduct of oil generation, will increase as well. So we're going to look at the trends. The world politics as well is changing. So what's happening around the world can affect, as it's a global financial climate, will have different impact. Climate change and CO2 emissions, quickly on this. Dangerous planet, I thought I would like to mention about it after the event which happened in Japan recently. The UK has a real potential to invest in renewable energy. So we'll look at what's the place of the UK in Europe. And sustainable development, what does it mean? What are the different criteria in order to make a project sustainable? So on the first slide, when we can see why this work, the legislation timeline, what I want you to show over this timeline is we've got different criteria. We've got the government targets on the top. We've got the legislation and the company targets. So this can be also summarized and led by the European Energy Performance of Building Directive, set up in December 2002, and the Energy, Climate Change and Planning Act in 2008. And what we can see from this diagram, this graph, we've got every different companies, we've got every different local authorities having different targets. So they either follow the national one or they follow their own. And each competitor, let's say we look at the bottom with Mark and Spencer, Sainsbury's or Boots, AstraZeneca, they've got all different targets and they seem to be racing against each other. So how can we address it? And every players in the industry are facing the same issue. How can they reduce their CO2 emission? Local authorities as well, with London, Huddersfield, 5 councils have also they've set up their targets twice higher than the national one. So we can see this. And then on the governmental target, reduce the London CO2 by 60% by 2025. UK cut CO2 emissions by 80% in 2050. So that set up the guidelines, the rules of the game at the beginning. We can also see from the slide on soaring oil prices since 1970 until 2008. Prices have been rising, dropping, but overall they've been rising dramatically. So if we look at, let's say, 2011, they can be even higher than that. So the main issue, what I wanted to show over this graph, is with the price of oil, of energy rising without knowing the future costs, how can we actually assess the right payback period for renewable energy? How can we actually advise a client if a renewable energy option is viable or not? And that's the big issue. Can we, let's say, if we take the price of oil since 2000, we might have a payback period of 20 years. If we take the price of oil in 2008, we might have a payback period of 7 years. So I'm just throwing different figures, but this gives you a bit of a flavor of the global issue on predicting the future trends. So as a result of this, electricity is a byproduct of oil, gas, coal. So we got wholesale electricity prices have risen dramatically. So we can see price of electricity generation increasing, and they are always increasing with the different generations. So we've got photovoltaic panels, which are coming into electricity generation, wind power, CHP as well. So again, how do we assess the payback period? Global political situation. So I'm going to go quickly over, like, let's say, the China forced to ration electricity. That was in May 2011. So different countries have to change their politics, and this can have an impact on the politics in Europe as price of raw material or fuel will change and will have an impact on the Europe trend. Inflation rate in the UK, as we can see on this graph. The demand is rising faster than the supply. Gas and electricity are by far the most volatile resource. So we look at different trends, so electrical and gas, communication, alcohol, tobacco, and CPI inflation. And we see different, all the volatility, the big volatility of the fuel. So I just went through, this graph shows how inflation rates for different categories can vary enormously. So firstly, gas and electricity prices are by far the most volatile. This reflects the volatile nature of supply. It also reflects the fact that demand and supply are inelastic. So see the volatile food prices for the economic theory behind this volatility. Despite the volatility, fuel prices have been rising faster than consumer price index inflation. This is a reflection of basic supply and demand factors. Demand is rising faster than supply. In particular, economic growth in Asia is creating additional demand growth. So again, global economy, falling prices of communications. So this was just at your leisure. So communication prices have often experienced deflation. This is probably due to the improvement in technology and perhaps increased competition, which puts downward pressure on prices. Alcohol and tobacco have been quite close to CPI inflation, so slightly higher in recent years. So the CPI is calculated by using a weighted average. If you spend a higher percentage of income on fuels than other items, your personal inflation rate is likely to be rising faster than CPI inflation. So for example, Age UK says the over 55s are an average of £30 per month worth of as a result of the rise in prices since September. And since January 2008, the average person aged 55 and over has experienced price increase at 5% above headline inflation. So the continuing impact of low mortgage interest rates has little benefit for those in later life, but energy and food matter more. So that's taken from the Independent. So from all this, this also shows the global trends outside the cost of energy. So looking now world carbon dioxide emissions, we've got the hockey stick effect on the bottom part of the slide. which shows basically like a hockey stick, a horizontal one. So showing for the past 1,000 years how the CO2 has changed, and the past 100 years how it has been dramatically increasing. And then billion of metric tons, so the world total CO2 emissions so since 2005, and the expectation up to 2030. Dangerous planet. So I just wanted to show this curve as like showing that if you don't invest in renewable, you might always be like if you're always on the grid, or you always are depending on other countries, you might be also at the mercy of Mother Nature with different earthquakes, hurricanes, typhoons, tsunami, wildfires, floods, draft volcanoes, tornadoes, blizzards. So this also have an effect on the global economy, with prices of insurance is increasing, prices of cost of energy generation. We see like back a few months ago when Japan was hit by the tsunami, we had we could see the change in cultural behavior, and also the impact over the world, with like, let's say, Germany also adopting and deciding to close their nuclear power station. But also on the good side, the world natural resource potential. So on the left, we can see the global wind map, and on the right, the photovoltaic solar electricity potential in European countries. So this is taken from the European Commission website. So we can see we've got a lot of potential in terms of renewable energy, in terms of generating our own energy. So why are we not using it? On the other side, we see the renewable energy in the EU, with the UK in 2005 was far behind at 1.3% out of the 15% targets. So back to the sustainable development, and to end this introduction, we've got what are the 3 pillars of sustainable development, so which led to this simulation and this work. So we see the environment, first of all, the society, and the economy. So I'm going to go back into the environment, which means probably carbon economy. How much can we count in embodied carbon, embodied energy? Then we look at society. So I transformed this society with because society can have it's difficult to monitor and to quantify in terms of numbers and figures. So I actually located, I won't cover this part too much, but I will replace it with energy at the same time. But this can be a further development of the work done. And then the economy, which seems to be, which is driving every investment so far. So the 3, if we manage to respect the environment, society, and the economy, we've got a sustainable development, sustainable project in effect. So this really shows you the kind of mind we adopted to carry on to start the project. So looking at the background of the research, what we looked at is if you want to actually consider sustainable development, reducing the CO2 emissions, integrating renewable energy, looking at the legislation, you need to consider those 8 items. So we look at Guide to Sustainability, which Guide to Sustainability and Low Carbon Design and Living, which look at how can we integrate renewable technologies and also change the behavior of people and quantify this in terms of CO2 emission. Then we look at Green Building Construction. It's looking at what are the techniques used, green building construction and existing low carbon buildings are also very important in terms of what does low carbon living means. And when we look at that we all live in buildings, the way we build, the way we refurbish building is important, the way we integrate renewable technologies in the buildings. But who is doing the job? It's actually the key role of consultants. So how do they deal with it? Most of the people who are in power in terms of consultancy at the moment are probably in their 40s, 50s. So how do they change their behavior, the way they design, in order to cope with this new trend? So this is actually part of the behavior as well. Existing design tools and British legislation. what are the different regulations available that we need to comply, and the existing tools to help the designers to integrate renewable technology. So as the last point would be the low or zero carbon energy sources. Which renewable technology can we integrate? How can we simulate them on every site around the UK? So looking at this background of information, the conclusion of this is that we've got importance of industrial buildings' impact on CO2 emissions compared to the public and residential and commercial. But there are no tools available, and the information is disjointed, which means the consultant who wants to integrate renewable technologies in the building will have difficulties, will have to make an extra effort, which will mean it will cost him more. It will cost them more, and they will be unlikely to spend this if they haven't got the budget, which means we'll miss on to the opportunity. So the aim of this project was, like, first of all, so identifying the difficulty to make informed choices about integrating low or zero carbon energy sources into new or refurbished buildings. So from this graph, we can see the feasibility, at the feasibility stage, from the feasibility to the delivery, we can see the effort in red compared to the benefits. And we can see, let's say, if at feasibility study, the cost of integrating a renewable technology might be £100 to integrate it. So the change of the building design might be £100. If we wait towards the delivery or detailed design, this might have been rising up to £1 million, which means that we actually fail on the opportunity. And if it's £1 million, you don't have any benefits to do it because your payback period will be too high. So the aim, the final aim, was to develop a tool enabling the optimization of economic, environmental, and energy savings in building. I'm going to discuss it through it. So from this graph, we start to see the project and how every project starts. We've got the client on the right-hand side, client who's got a project. This project has got different indicators depending on what's the motivation of the client. Is it improvement of capital cost? Is it reducing the CO2 emission? Is it improving his image? Is it promoting environmental responsibility? Improving his environmental protection? Avoidance of environmental impact? So we don't really know. Every client has got a different motivation. And on the left-hand side, we can see the engineering stress, which is which renewable technology can we integrate, how much can they generate in terms of energy or water, how much do they cost, and how much CO2 do they emit. So the tool actually looks at this overall view and try to find a compromise in the middle, as we can see the middle arrow between objectives and targets. So the philosophy and the strategy of sustainability is from the optimization of the tool. It's actually looking at reducing the energy demand at the beginning of project, the most important before integrating any type of renewable technology. So this can be from site analysis, building orientation, passive design, also natural daylight, glazing design, insulation, and then air tightness, heat recovery. But also the next stage, start to look at meet the end use demand efficiently. So which type of equipment are we going to use to get the most out of it? So we start to look at the performance certificate of equipment with the ABC rating, and we try to get the optimum equipment to be integrated into your building. Once we've got the reduction of energy demand and selected the optimum technology, kind of end-use demand efficiently, we want to supply from renewable technologies, so low LZC, low or zero carbon energy sources, which are like each individual ones, solar water heating, can we integrate them, wind turbine or photovoltaics or biomass or ground source heat pump, trigeneration, rainwater harvesting, or passive solar air heating. But this is, at this point, I think most of the consultants actually stop and then don't consider combining the different technologies, because then it starts to become a bit more complex and more time consuming. So what we're looking at is combining the different renewable technologies. So how can we combine ground source heat pump with solar water heating, with photovoltaics? How can we select these combinations? So we're going to look at the combination side and the supply from renewable technologies. Then the project gets built, and the last link to this process is enabling the energy management. So metering, data analysis, reporting via the building management system. And then this will feed back eventually to the next project, so through reducing the energy demand. So it's acting like a loop. So the optimization tool is actually looking from reducing the energy demand to the combination of different renewable technology. How does it work? For each renewable technology, so on the left-hand side, we've got the performance analysis of each renewable technology. So this can be given through either technical parameters from the manufacturer or from internet as well, open sources, guidance books, rule of thumbs. And on the right-hand side, we've got the LZC, so low and zero carbon energy, resources. So what are the meteorological data available in the UK or in the world if you're listening to us over the other continents? What are the different maps and local resources that we've got? From this, we can start to look at an equation, at setting up an equation for each renewable technology. So steady state or transient thermal simulation. So in effect, it's creating an algorithm which will enable to set up the parameter of the renewable technology and use the meteorological data from each site around the UK or around the world. Then from this algorithm, we can find the delivered low and zero carbon energy. So the database for simulation work that we can use are actually like from the Met Office or from the NASA website or from the CIBSI weather data. So some of them are free, others are you have to purchase them. And what are the different type of information we're looking for each renewable technology? So we can start to look at dry bulb temperature, wet bulb temperature for different thermal heating or cooling simulation, cloud cover for solar simulation, global solar irradiance diffuse for the solar, average rain per day for the rainwater harvesting, wind direction for wind turbine, and so on. We look at each renewable technology. So we decided to start with 8 technologies. So passive solar air heating, solar water heating, wind, solar photovoltaic, ground source heat pump, trigeneration, biomass heating, rainwater harvesting. But we can go beyond this and integrate as many as we want if we decide to. So looking at the methodology, we start to input the data at the beginning. So this data would be the size of the building, the usage parameter. So this becomes a bit complex, so I'm quite happy to actually discuss it later on if there are any questions. But I'm going to go briefly through it. We've got data input, so what are the site geometry, site data. Then we look at the building energy demand estimation. So this can be, in effect, set up onto a graph which shows like the location and shows the daily heating demand or cooling demand versus the solar energy supply or the different parameters. We can see from this graph that comparing Edinburgh against London, somebody in Edinburgh will pay more on gas bill, but than London because they'll have more heating demand. But on the other hand, like the building, the project in Edinburgh will have less solar energy, which means that if you use solar energy in Edinburgh rather than in London, you'll use more solar energy in Edinburgh than in London. So more of the solar energy available. So passive, so then we start to look at each individual technologies. So passive solar air heating, solar water heating, solar photovoltaic, wind, trigeneration, ground source heat pump, biomass heating, rainwater harvesting. Integrating it into the building energy model. So what is the energy supply versus the energy demand? Then we start to combine the renewable technology. So we go into the row n number of combination options, and then starting to look at optimum in economy option or environmental option or optimum energy option. So again, if there are any problem, any issue through the simulation where few options are not the right one, we can go back into the loop. So I show it here on the left-hand side. Assess the constraints of the site and feed back into the simulation. And then once the constraint solution has been assessed, we can select the preferred option to go forward. So the results of the simulation can be displayed as electricity generation. So I take, for example, an hourly average energy generation for solar photovoltaic or wind. So for May, June, July, August. But we also can go monthly graphical analysis, so comparing the impact of each renewable technology versus the demands. The demand is shown in red, so the top graph is showing the energy demand and energy generated for the heating. The bottom one is showing the cooling demand. And then we can see, so the red line is the demand, and the green line on the top are like the biomass, ground source heat pump, and solar water heating in brown. Then the bottom one will be the same. So you compare the cooling demand versus the cooling by using trigeneration or ground source heat pump or combining both. And then you can also do the same with electrical demand versus generated. So this can use photovoltaic or wind or both versus the electrical demand of the building. And the water demand versus harvested. So the blue line shows the amount of rain collected, and the red line shows the amount of rain and the amount of water needed. So this is actually a way to explain, to visualize the impact of renewable technology on the building energy demand or project energy demand. So this is looking at each individual. So now we're looking at combining the different technologies. So what we've got here is different renewable technologies for each renewable each type of renewable technology. We could have different manufacturers. So I've done an exercise. If we have like 50 type, so if you look at n, the number of LZCES available versus the group size, if you've got 50 renewable technologies available, and you want a group of 20, you've got 47 trillion combinations option to select from. So how can you select the optimum one when you have an hour or a day to do it? That's where I wanted to look at. We also consider when you consider like the financial, the banking industry. I've got different type of models to assess what is the most risky investment. On the engineering side, we generally don't go that far. So I wanted to combine these two knowledges and use it for the engineering world. So what we start to look at is the combination assessment. So let's say if we take 4 technologies, so this is a print screen of the tool. So we take 4 renewable technology by different codes, so it's like letter code. So A for passive solar air heating, S for solar water, G for ground source heat pump, and T for trigeneration. If we take 4 renewable technologies and we want 3 renewable technologies at a time, we're going to have 4 combinations. So the graph, the result, the table of result at the bottom shows the philosophy adopted. So looking at the energy potential generated, so heating, cooling, electrical, water, versus the energy saved in economy and capital cost, annual maintenance cost, and environment. So this is a brief view of the methodology and philosophy of the tool. Now I'm going to go on to a case study. So for a project, let's say a dwelling or a non-dwelling, I've got the same, so the non-dwelling will be more complex and more time-consuming than the dwelling, but the philosophy and the strategy is the same. So we want to know what are the design parameters, so the usage factor of the building, how many days, how many hours, to know what is the behavior of the people living in the building. Then we also want to know the total building footprint. So this enables us to actually start to look at different rule of thumb. So let's say how many watt per meter square of lighting in terms of heat gains, or how many occupants have we got in the building in terms of how many computers are we going to have, how much water will be used. So the total building footprint can be used for electrical demand, heating demand, cooling demand, but it can also be used for like the amount of space available on the roof to know how many solar panels can we install, what would be the capacity of the roof. So we also want to know the total land footprint, so how many meters square of land have we got around the building. So this can be useful if we, let's say, haven't got enough space on the site, on the building, to install the total capacity of solar panels, but also to know how many boreholes we could actually drill into the site, how many kilowatts could we extract from the ground and could we use into the building. So from this, we get one of the most important output that we want to know are the electrical demand, the heating demand, the cooling demand, and the water demand. And electrical, heating, and cooling, we are interested to know what are the peak demand, but what we are most interested are how many megawatt hour are used for a year or a month or a day. Because the megawatt hour is a better, more respective unit for renewable technologies. So without renewable technologies, we start to simulate the heating, cooling, electrical, and water demand. So this can be seen on the bottom table on the code, so HBD for heating building demand, CBD for cooling building demand, EBD for electrical building demand, WBD for water building demand. So sorry, it's a bit crammed onto the screen, on your screen, but I try to actually get all the information. That's why I used abbreviations. So we've got a color code with different colors. So the blue for energy input and finance. Output for finance will be in orange, and then output environment will be in green. So the first part would be to integrate what, first of all, from your consumer, how much does your consumer or your client pay for his heating bill? What is the primary source of energy? So how many pence per kilowatt hour? Then electricity will be the same, cooling, and water. How many pounds per cubic meter? And then for biomass fuel, how much would it cost per kilowatt hour? Then we start to convert this in terms of real cost, which means using the efficiency of each individual energy generator. So we look at, let's say, using the SAP efficiency, we start to look at 78% efficient boiler, or 300% efficient cooling unit, or 90% electricity. And when you start to look at the real cost of 1 kilowatt hour, you realize that there are some losses. So 1 kilowatt hour of heating can be different than how many kilowatt hour you're going to have into your building demand. So it's cost versus energy conversion. So then the last part of the table is looking at how much heating we need, cooling we need, electricity we need, water we need. What would be the capital cost to buy like a boiler or a chiller or connecting to the grid, or a water tank, water storage, or water maintenance. And then the annual maintenance. So again, how much do we need to invest to maintain the equipment? And the annual cost, so in terms of running the equipment on fuel. Then I wanted to just show like cost-saved economy. So with the different incentives, there are no incentives, there is no payback, and there is no payback with incentive neither. We look at the environment, so it's the same type of table, but with the environmental impact. So how many kilograms of CO2, how many tons of CO2 have been produced to actually generate or manufacture the equipment. So that could be the embodied carbon or the embodied energy, how many kilograms of CO2 or how many kilowatt hour of energy have been invested to produce one gas boiler. And then the environmental impact is how many kilograms of CO2 have been emitted to produce the total heating demand or cooling demand or electrical demand or water treatment. And this can be taken from either the carbon trust or energy saving trust date figures, or of GEM, of Watt, which can give you the DECC as well, can give you the different figures and give you how many kilograms of CO2 are emitted per kilowatt hour of energy. So from I'm going back onto the middle table, like the top table, where we can see heating with gas would emit 0.194 kilogram of CO2 per kilowatt hour. Heating with electricity would use 0.544 kilogram of CO2 per kilowatt hour. Then for water is a bit of a different one. Like for every cubic meter of water that you use, you also need to treat it. So you need more energy as well. So this also actually has an impact also in terms of when you're going to select the renewable technology. If you have like gas boiler versus heat pump, you'll start to see that you need to have an impact on your COP, because obviously the heating with gas will use like let's say 1 kilowatt hour of gas uses 2.5 times less CO2 emission than using 1 kilowatt hour of electricity. Then when we start to look at renewable technologies, so we start to look at biomass, air source heat pump, ground source heat pump, photovoltaic, rainwater harvesting, solar, water heating, trigeneration, and water. And start to look at what would be the impact if we try to integrate as much energy into the building as possible. Then we start to look at added capital cost and added maintenance cost. So when I describe added capital cost and added annual maintenance cost, I mean the added capital cost compared to a classical system. So let's say if your biomass boiler enables you to replace 50% of your gas boiler capacity, you shouldn't add a straight cost to your project. You should subtract your total boiler cost by half of the gas boiler cost. So that's why I consider it as added capital cost. And then added annual maintenance is the same. So would we need more maintenance than a normal system? Then we start to move at column cost saved economy. So how many pounds are we going to save by not using conventional fossil fuel energy type? Cost save economy with incentive. So what's the difference between without incentive and with incentive? How much benefit do we get? And then we look at the financial payback and financial payback with incentive. So these data are like indicative. They are not they are not predicting the future. They are just as an example to see what would be the likely optimum option to select. But then from this type of data, if we have different options, let's say we could actually start to create different scenarios and have different type of inflation. So 3% or 6% or 7%, different type of energy, and then we can play with different figures. So for those one, I just decided to take the worst case scenario and get a constant cost of energy. We can discuss a bit further, but I found this slide is already full of information, so I didn't want to put too much. We look at then the same with embodied energy, reduce environmental impact. So on the green side, what I mean is that we have different guides. So there are a guide called so the Green Guide to Material Specification from the BRE, which can be used. But this one actually used A, B, C rating. So it's not really, it's a bit harder to use quantified figures. But another guide that I quite enjoyed was the ICE, so the Inventory of Carbon Embodied by the BISRIA and done at Bath University. So this is an inventory of like a few thousand material and give you some raw figures. So the carbon industry is quite new, so it's only starting, and we need more data to actually feed into this tool. So that's why this tool is a bit probably too innovative sometimes, and that's why it's struggling for the data to be fed into it. Then we look at software results. So from the previous slide, we could see actually each individual technologies and what are their impact. Now I'm starting to go, okay, we know this information now. How can we go beyond this point and further improve this? How can we combine the renewable technology? So we look at, let's say, 5 or 6 technologies, and we want 3 at a time. And then the tool will actually start to simulate each combination for you to actually look at what are the impact of each combination into your simulation. So what will be the impact on your heating demand, cooling demand, electrical demand, water, on the capital cost, the maintenance, annual cost saved with the incentive, the payback, and the payback with the incentive. And you can actually compare. So again, these figures are indicative, and they enable you to have a feel of what will be the likely optimum combination for your project. You can also, if you have too many combinations, you can use a good option, which is like Excel-based, which is ordering the result by columns. So if you want the optimum cost or the optimum energy, you can select which column you want to order, and you will order your entire row in terms of optimized energy solution. This slide shows exactly the same, but with the environmental impact in terms of CO2 emission, energy, and in terms of energy to produce, so embodied energy, embodied carbon, and energy used or energy saved for the renewable technology. I wanted to finish with this last one, which is actually a way of displaying. So when you have a client and you want to actually show what is the impact of his investment of renewable technology, you can look at. So I wanted to show here like the capital cost as a red line, so a constant line, and then the return without feed-in tariff, so in green, and the return with feed-in tariff. So after 25 years, you can see the end of PV system life and feed-in tariff agreement. So we don't generally really know what's going to happen to the photovoltaic panel after 25 years, but it's likely to be still working and producing some energy. So I just showed it on the production. So without feed-in tariff, you would get something like 60 years. And with feed-in tariff, you would get a figure like 8 years, 8 to 10 years. So from this, you don't stop at this point. What you also want to show your client is actually what is the impact of each variable. So what would be the impact of your investment if tomorrow the inflation is rising by 2 or 3%, and you can start to give different scenarios. So I showed it in tiny little lines in blue, and you can see like different examples. So this could be either with price of energy rising or decreasing, price of inflation rising or increasing, and other type of impact. And you look at these different scenarios could be adopted for without feed-in tariff, so investment without and investment with feed-in tariff. So on this way, you're actually giving an open solution to the client, and you can actually decide, let him decide what would he want as the best solution for his project, and what are the likely risks involved for each investment. What would be the payback return? So that's the last slide with different pictures, different slides, different part of the last graph again, theoretical life period. That's the end of this presentation. Thank you for listening. Thank you, Branka and Craig, for organizing the event. And I'm going to pass on to Branka now.
Thank you very much, Aymeric. Unfortunately, we do not have questions from our audience, but we still can ask some questions. Douglas, could you tell us, please, what is GeoCapita doing in general in relation to sustainable built environment, and then how this project links to that wider program will work?
Yeah, thank you, Branka. It's a very good question. GeoCapita is a very new company, but it's grown out of a concept which we've had for some time around a response to both the ecological crisis of increased greenhouse gas emissions and climate change, and the economic crisis. And as a response to these twin crises, we have developed a model which is a hybrid approach to sustainable community development. By hybrid, I mean that there is a mutual fund within our groups, in other words, a cooperative, and there is a commercial entity. So what we are seeking to do is to assist our clients, or as we prefer to see them, our partners in Scotland, in the rest of the UK, and indeed internationally, to develop sustainable communities. Sustainable communities includes sustainable housing, by which I mean affordable and low carbon and low energy utilization housing. It also includes renewable energy, building mounted renewable energy, community scale renewable energy, sustainable transport solutions, hybrid vehicles, electric vehicles, recharging of electric vehicles, flex fuel vehicles, and environmental protection projects around land remediation, pollution cleanup, climate change risks, and so on. So GeoCapita is a rather unusual structure, but it's specifically structured to respond to those twin crises, the ecological and economic crises, by providing an alternative solution to how local communities can develop their own sustainable projects. Sustainable housing, sustainable transport, renewable energy, environmental protection, and coming from those local community-led initiatives, how to regenerate economic growth and real employment opportunities at the local community level. So this is the original conception behind GeoCapita, and coming from that, therefore, it is natural for us to seek to work with universities and other centres of leading research into energy efficiency in the built environment, and hence our desire to find a way to work with a university such as Edinburgh and Napier University to develop some specialised methodology for analysing the performance of buildings and to enable those partners that we are engaging with, primarily local communities, to improve the performance of their existing housing stock and to improve the renewable energy optimisation of new build. And it was very fortunate for us that something such as Kickstart exists, and it was a way in which that early stage funding could be provided for Napier to actually provide that solution for us.
Thank you very much, Douglas. When we advertised this event, we received a question from USA, from one of our members, who asked the following. I would be curious if the model shows the impact of the property tax on improvements. In many jurisdictions within the USA, any improvement that adds value to the building results in a higher assessment. That higher assessment results in a higher tax bill each and every year that the improvement adds value to the property. Thus, over the useful life of an improvement, a 1% or 2% property tax could have the economic impact of one-time sales tax of between 10 to 20%. Does this model account for this added expense associated with making energy efficiency improvements?
So that's an excellent question. Thank you for asking. The model, because I actually did it for the UK, doesn't reflect this type of simulation, but it's very extremely flexible and everything, because each individual who will want to use this software will be from different background, will have different jobs, and probably will want to do different things. So this can be adapted very easily. And that's why this is like an Excel-based software. But I started to look at this type of simulation into the financial side. That I wanted to show it on the screen. This would have been like probably a further 10 rows, 10 columns on the screen, which couldn't show it. But we're happy to look further behind this. I never heard about this tax before, and again, like the assessment on the future price of the future value of your building once it's got the renewable technology I think is very volatile, because it's very dependent on who you're going to sell it to. If somebody is keen to have renewable technology, or if somebody really find them ugly, let's say, for different renewable technology. So that's an open answer, to be honest.
Okay. Could you tell us, please, if this software is available publicly?
So this software at the moment is available. So it's not available publicly, because it was developed as well, like to help GeoCapita. So if you want further information, if you want to have more help, and you would think this can be used, I would suggest either contact me or GeoCapita or Douglas to discuss further. If you're happy to invest to develop this software, you find it's got some great potential, please do not hesitate to get in touch.
Have you published any papers on this software?
I've actually published 3 papers, and I've done 50 different conferences around the world, in South America, in Asia as well, in Africa, and all around Europe as well. And I found very, very positive results, and also resulting in 9 different awards, international awards, either academic awards or professional awards, or marketing awards as well.
We would kindly ask you to provide references to these papers, so that if our audience is interested to find out more, could you, I think that this tool could be applied both to existing and new buildings. Have you done any case studies on existing buildings, real case studies, or?
I've done different case studies on real buildings at the same time. I've done monitoring of a dwelling as well, so monitoring every minute for a month and simulating the building, the energy demand versus the energy simulated, and found very close result by 10%. So this can be used, but again, in terms of simulating and comparing against real life project, this is a frequent question, and because it's actually really difficult to estimate the future of your investment. It's actually hard. It's a bit going to ask to a banker to invest £1 million of your money and guarantee him to get a 30% return over the next 25 years, and the banker will never tell you that it's possible. So it's because it's depending on the future trends of inflation, of energy cost. It's an indicative tool. It's an energy decision-making tool for the time with different scenarios.
How do you see possible future development or research related to this tool?
So I can see different, many PhDs coming out of this simulation, where there are many corners that I didn't have time to go through into this project. I can also see probably different partnerships with different governments or other simulation tools. Investments as well are important to update the database, as well, like from the manufacturer portfolio, as well as the weather station data, and looking at worldwide usage of the software, if other continents would find it useful, as they did from the different conferences.
How would one select a renewable technology mix on a site by using this tool?
So from using this tool, you need to look at first of all, like the previous, I think it's like the past 10 slides, which shows on the case study. So if you want to actually look at your site, you need to look at what is your site geometry, so the site size, the building size as well, and then what would be the assumption in terms of usage, energy demand, and then start to use the different combination possible. So this can be using this software or a handwritten software, but this can take probably many months or many years in the other case. So please do get in touch if you've got any project and you're interested. We can discuss further.
How do you simulate each renewable technology energy generation potential?
So each renewable technology can be simulated using either individual software tools for each renewable technology, or you can actually use online websites which give you an estimation of renewable energy potential, or you can also contact a manufacturer or a trade association of each renewable technology, which will give you an indication of what is the potential energy generation, natural energy generation on your site.
Mm-hmm. And where do you get cost of different technologies?
So the cost for different technology can be taken either, so the SPONS book, which is a cost consultant book, can give some indication. Otherwise, you can have different BizRIA guides for indication on cost, rule of thumb. But the one that I prefer personally is contacting individual manufacturers, because the price of these technologies are changing all the time. So I would advise to really consider contacting a manufacturer with the updated last prices that he's got.
And is information or are the estimates on embodied carbon CO2 in materials available also on embodied energy?
So these estimates are actually, as I said, it's very innovative on this side, and people who've got their carbon calculation tend to keep them privately and not share it publicly. So the guides that I gave, the IC from BISRIA and the Green Guide to Material Specification, are actually official document that you can use. They give brief indications. I know few manufacturers of renewable technologies have started to calculate how many kilograms of CO2 are emitted to produce their technology. Most of them haven't done this yet, but hopefully in the next coming years, this will start with the low carbon economy kicking in.
Okay. And how do you advise clients on future financial trends, on payback period, on inflation, fuel costs? These are all very changeable variables.
That's that's an excellent question. And again, this can be used. This can be actually estimated through statistics from previous trends. So if you look at the UK financial trend over the past 100 years or 50 years, you can look at the price of each renewable technology, the price of inflation, the inflation rate of every year, and start to say, well, the cost of energy and fuel has always been rising for the past 50 years. So why would it start to drop now when the demand is increasing? The third world countries are having a higher and higher level of life. So it's actually, it becomes stronger assessment and stronger assumptions for the project. So, but again, giving a different, because the payback depends also on the cost of the technology. The cost of the technology seems to be decreasing more and more as it's an effect of economy of scale, and the cost of energy is increasing. So the price of conventional energy generation versus renewable energy generation are going to meet in the next few years, and this will help also on the CO2 emission side.
Okay, well, thank you very much, Aymeric, and we wish you to find investors in your for the development of your software tool in future. Thanks very much again.
Thank you very much.